Okay, the next session will start. So please come in.
Yeah, let's go. Okay.
Oh, for the next session, we'll start it right now. Ready? Okay. We'll start the next session right now. So the next session will be architecture extensions, accelerators, and fault tolerance. So of course, there's many topics, four interesting talk in this session. I'm the session chair, Mingyu Gao from Tsinghua University. So first we'll have our first talk from Rodrigo Sukuski. So he's a second-year PhD student in the Federal University of Paraná, right? Yeah, so his research interesting mostly on processing memory, and as he will talk about in this talk, OpenPIM, standardizing in-memory processing with RISC-V vector instructions. Let's welcome.
Thank you. So, hello, my name is Rodrigo, and today I'm here to present our work, the OpenPIM standardizing in-memory processing with RISC-V vector instructions. Yes. Starting, this figure taken from the shrink paper illustrates the growth in the number of instructions for some instruction set architectures over the past few decades. In this period, the number of instructions from the x86 architecture tripled, due in large part to vector extensions. In the same period, despite its encoding differences, ARM also made a leap, caused by the same reason. But what is the problem with those vector instructions? Here in the horizontal, we have the evolution of Intel vector extensions, and in the vertical, we have the number of vector instructions added to the processors in this period. Initially, in 1997, 48 instructions were included for 64-bit vector processing. Then, a few more were included for 128-bit processing, and a few more, and after that, a few more. And here we have this unsustainable trend. And that's because this kind of vector instructions only operate over vectors of a fixed size. So, new instructions must be included for each new vector size added to the architecture. And due to some commercial wars between Intel and other companies, we had that unsustainable growth. But there is an alternative. Vector extensions like size-agnostic vector extensions, ARM SVE and RISC-V vector extension, only define a maximum vector size. So each instruction can operate over vectors of up to that maximum size. Following this idea, the RISC-V vector extension with a reduced number of instructions can operate over vectors of up to 64 kilobit. But how this is done? So here we have a RISC-V binary containing vector instructions. This binary can be executed on different machines independently of their maximum hardware vector length. Let's suppose this is a loop containing some vector instructions. This kind of loop is controlled with information regarding the current vector size of the architecture. So, at each loop iteration, the software informs the hardware about the width of the elements operated and the number of remaining elements to be operated. Then, the hardware informs the software about the current vector length that is defined based on the number of remaining elements to be processed and the maximum vector size of the architecture. This information is used to control the loop iterations and its reminders. Okay, but we'll still have a problem. Processing large vectors requires huge data movement, and regarding energy, this data movement can consume up to 90% of the system energy. This is due to some application parts with low data cache reuse that requires many costly off-chip transfers. Also, regarding performance, applications with data streaming patterns can remove useful cache contents, and this can lead to more slow off-chip transfers. One solution to this problem is the near data processing approach. Starting from a usual von Neumann system, this approach consists of inserting some processing units closer to the memory, thus with low latency memory accesses, and direct access to the row buffer locality, so all the data loaded by each load. And by doing this, we can reduce some of these costly data movements. But this approach also has some problems. Here, in the horizontal, we have classified some near data processing devices according to their instructions, between those with only simple instruction set architectures and those with full or complex instruction set architectures. While in vertical, we have classified them between those with only scalar operations or vector operations. And here we have some of those devices. No problem. Okay, thank you. So each group corresponds to a different programming model in this near data processing ecosystem. And starting from this, our objective is we have a starting masked near data processing ecosystem. We want to standardize the way of accessing those devices. And for doing this, we have selected the RISC-V instruction set architecture with vector extensions. So, over these ideas, we have developed a simple initial mechanism to show our ideas. So, starting from our usual von Neumann system with a main bulldozer CPU, this simple system adds a simple core close to the memory, or Mickey Mouse core, with the same instruction set architecture as the main core. This near data processing device has low latency memory accesses, and by using large RISC-V vector instructions, can take advantage of the row buffer locality in the DRAM, and thus can reduce the costly off-chip transfers. So, in application, would have portions of its code selected for in-memory execution, with low latency memory accesses and direct access to the row buffer locality. Let's see a first execution example of this idea. So here we have a vector sum application. This application would be normally compiled, and if a portion of the application is suitable for in-memory execution, the compiler can add traps to warn the operating system. Then, during execution, the application starts executing in the main core. The trap warns the OS about possible gains with the in-memory execution, and the application is migrated to our in-memory core. When convenient, it is migrated back to the main core. So, what are our key ideas here? First, do not change the source code of the applications, just making minimal changes to the binary code. Also, do not include any new RISC-V instruction. Just use existent RISC-V instructions. And process some application parts close to the memory with low latency memory accesses. And finally, use wide vector operations in order to take advantage of the raw in-memory parallelism. Okay, but how should be our in-memory core? Here we have the sonic boom configuration as proposed in their paper. Let's take a look here. An in-memory core could have first the size of its buffers reduced. We can also reduce the width of its stages and remove some cache levels, keeping only its first cache level for some data reuse, but still with low latency memory accesses. We can also reduce its frequency in order to meet in-memory thermal constraints. And we can improve its functional units by adding large vectors processing inside it. Well, however, in order to maintain compatibility with the main core, in our approach, we cannot do this. But that's okay, because we are adding wider cache lines to take advantage of the row buffer locality. So, regarding our related work, here we have selected some work regarding in-memory processing from the last years. Some of them already propose the use of the same ISA as the main core, but others require custom ASAs and APIs. There are also papers that use vector operations inside the memory, and others that just use scalar operations. Usually, those do not include just a single in-memory device, but this requires data exchanges and complex coordination between those devices. Some papers also do not require source code modifications, and the ones that do can place a burden on the programmers for the use of the in-memory device. And despite some of them being implemented to the main memory, others are implemented in specialized cores or specialized cache levels, specialized SSDs, and so on. In this context, we aim to provide general applicability with ease of use and reduced overheads. Based on this initial mechanism that is proposed to showcase our ideas, we have some preliminary results regarding a vector sum application evaluated in our in-house SQL Accurate simulator. So, in the vertical, we have our speedup regarding usual execution in the main core. This main core is configured according to the sonic boom configuration with the vector extension. Next, we have our approach with the same main core and a superscalar in-order in-memory core. Each result corresponds to a difference in-memory system with a different cache line size. And initially, just by using this in-memory core, we already can achieve some speedup. This speedup increases as we increase the cache line size, and the raw in-memory parallelism use. So this can reach up to 3 times speedup in this perfect example. We are currently working on these ideas for a paper in the next ISCA, but there are still some open questions. First, how to reduce cache coherence between our in-memory core and our main core. Also, how to decide what is the best portions of codes to send to our in-memory core, and when it's the best time to make the migration to the in-memory core. For future work, so here we have this masked near data processing ecosystem. Some of those devices could be adapted with relative ease for our ideas. Let's see from another angle. So here we have classified the same devices between their, according to their distance to the DRAM cells. While in the vertical, we have classified them between general purpose devices or accelerators. And those are the devices. So this is the area that could be covered by our work. For future work, we need to cover papers that use DRAM cells to make processing, custom accelerators, and devices outside DRAM, the custom cores or specialized cache levels. Now, a little bit about us. We are part of the HYPES group from the Federal University of Parna. My name is Rodrigo. I am the second year of my PhD. And this is my advisor, Professor Marco Zanatta. He apologizes for not being able to be here, but his wife is 40 weeks pregnant and about to deliver. If you have any questions, suggestions, or idea, you can send us an email. And now, I'll be glad to answer any of your questions. Thank you.
Okay, so any questions from the audience? Just to, yeah.
Thank you for the presentation. I have a question about parallelism. So if you have any plans or if you have considered already, but doing these operations in the secondary CPU, like the Mickey Mouse CPU that you said, while you're doing the main operations in the main CPU. So if you could like somehow trigger the memory operations before they are required so that this can be done in parallel.
Well, let me see if I understood your question. You asked, I can see two things coming out from your question. First is how to deal with parallel applications using the in-memory device. And the second is why to use the in-memory device if you can just prefetch some data accesses.
I mean, it's kind of like you know that you have to do this data operation. So in the example of the vector sum, so you know that you have this operation that will require that you do. So if you can continue the processing in the main, because you use a break, right? So you stop the processing so that the Mickey Mouse processor can do the in-memory operations, right? So if you can do both things simultaneously, not just breaking the processing, but continuing processing while the other CPU, the one that is close to the memory, is doing its thing, right? So
yes, this is an alternative. There are really, I've read this week a paper that do this, and this could be implemented. In this first attempt, we are just trying to make the simplest core that could have this idea. And in order to just select portions of the application and just migrate to another core without having to speculatively execute instructions, this was the approach by now. But this is a great path to the future.
Okay, thank you.
Thank you.
Any more questions? We may have another short one. Okay, so I have a quick question. Like for the compiler part, like what specifically? Because since you are executing the RISC-V instructions in memory part, right? So does that have like some other like different demand on the compiler optimizations? For example, you may optimize for like a wider vector or like more aggressive parallelism or other things in the compiler side to really boost your performance for the in-memory core. So what's your consideration? I think it's part of your future work, right?
Yes, but we see that one of the great advantages of the vector extension is just this ability to operate over vectors of different sizes. So the same compilation can just be adapted to different systems. But we see that when we are operating in the memory, we need to take advantage of this large row buffer. So the optimizations that we usually made for caches aren't so
not that important.
Not that important anymore. Yes, and we need to think in another granularity for each problem. But yes.
Okay, cool. Okay, so since time limit, so let's thank the speaker again. Okay. Okay, so the next talk, our second speaker is Professor Fengwei Zhang from the Southern University of Science and Technology in China. So Fengwei is an associate professor at the Southern University of Science and Technology in China. His primary research interest lies in system security with a focus on trusted execution environment, GPU confidential computing, debugging, transparency, system instrumentation, and hardware-assisted security. So the talk he will give is about trusted execution environment, about the details of the design and implementation. So let's welcome.
Okay, thanks Mingyu for the introduction, and hello everyone. This is Fengwei Zhang from Southern University of Science and Technology, and it is a great honor for me to be here to present our work, Trusted Execution Environment Design and Implementation. So before I get started, let me briefly introduce what is Trusted Execution Environment. So as we can see that Trusted Execution Environment, or called TE, is a hardware-assisted security design to protect sensitive data in use. Okay, and actually we can use TE applied both on cloud and edge devices. And also for Trusted Execution Environment, we have multiple hardware vendors already supported. For example, Intel have something called a software guard extension, SGX, and also it has another thing called a TDX. And AMD as well has the SEV, and ARM also has a similar technology like TrustZone or CCA. So in general, we have three types of trusted execution environments. First type is called application level. And basically, we can run a trusted enclave and in the application level. And a similar product like Intel SGX is application level TE. The second type is virtual machine-based TE. Similar technology like AMD SEV, ARM CCA, they all belong to the second category called VM level TEs. The last one is called a system-level trusted execution environment. For example, we can have a similar technology like ARM Trustle. Actually, is a system-level TEs. They can split the CPU into two modes and to do the context switch. All right, so in our lab, we have done a few works on trusted execution environments. Here, we just list a few papers we have published in the last 3 years. In today's work, I'm going to focus on a few works we have done in our lab. The first one is called COFR, a RISC-V TE without customized hardware. So before we dig into the details of the TE on RISC-V we built, let's take a look at the state of the art. So for the current trusted execution environment on RISC-V architecture, we can briefly categorize into two solutions. The first type of solution is a hardware-based approach. And basically, it will introduce actual hardware, and similar work we can see is like a Timber-V, POL9, like Hyper-T, those kind of hardware-based solutions. The pros is they can provide efficient and scalable trusted execution environment, and also have some limitations such as incompatibility, ecosystem fragmentation, etc. Okay. For the software-based approach, it's basically built on top of RISC-V ISA specification, example like Keystone and Virtual Zone, etc. Okay, the pros is say they have a good compatibility and they could be widely deployed. However, the limitation is including they don't have a good scalability and they don't have a good performance overhead. So those are the limitations. So the question here is how to design a scalable and efficient RISC-V TE without introducing actual hardware. So that's a key question we want to answer. All right, so here let me introduce you a briefly overview of the Coffer system we built. And basically, we just modify the secure monitor, and we try to achieve the scalability. And also, we propose a concept called a logical PMP, which is a PMP virtualization solution, and try to create abstraction for those kind of memory, and then we can achieve scalability. Also, we have a concept called E-modules. Basically, we can do the dynamic trusted computing-based reduction, and also we can modular design and dynamic loading. Okay, so let's get into a little bit details about what is logical PMP. So basically, as we know, for the PMP on RISC-V, it has a number of registers, and we also can isolate a limited number of memory regions. So in order to overcome this challenge, we basically virtualize the PMP and try to use the LPMP to do the virtualization. So in that case, we can have an unlimited number of memory regions could be isolated by our solution. Okay. And also, we do the further optimizations. For example, we reduce the trap frequency. We also introduce instruction PMP and data PMP. So in that case, we can have a better optimization in terms of performance. So in a short conclusion for Coffer, basically the Coffer is trying to build a trusted execution environment which can achieve 3 goals. First, we want to achieve compatibility. Second, we want to do scalability. And last one, we want to be efficient. So that's a short conclusion for Coffer. Okay, next I'm going to move a short introduction on a GPU TE that we built recently. And as we know, we have multiple vendors already supported the trusted execution environment on CPU. However, due to the recent booming on AI, and there is a need for us to build a trusted execution environment on GPUs. Okay, so as we can see for the GPU security, we can have multiple data actually running on the GPU memory. And those GPU memory also could be threatened by other attackers. So to do this, we actually try to adapt the existing solution to GPU. However, there are some challenges. For example, we can from the architecture level, the architecture is different, and also the TCB, there could be a problem, and also the compatibility also could be other issues. So in light of these problems, we build a system called a Strongbox. Okay, Strongbox actually is a GPU TE, and which leverages the existing hardware features, such as ARM trust zone, address space layout randomization, and also the stage 2 translation. And also we do the shared memory between the CPU and the GPU. Okay, so the figure shows the brief architecture for our system. And more importantly, we actually don't introduce new hardware in order to get the compatibility. Also, in order to do fine-grained memory access control, we actually combine the stage 2 translation, which is a page-level granularity, with the TZSC, which is a hardware feature on ARM. And it can give us a slot granularity. Okay. Okay, let's do a short conclusion for Strongbox. Strongbox is the first GPU TE on ARM endpoints. Actually, it can ensure secure and isolated computation on ARM endpoints. And also, it can maintain high compatibility. We also have the Strongbox source code open on GitHub. So if everybody interested, please feel free to download it. Okay, let's move on. So as we can see, we can build trusted execution environment on GPU, right? However, for those GPUs also could be vulnerable to some attacks. So today, I'm going to introduce you an attack we recently found. Actually, it's called a Moreaes, which is breaking GPUs with GPU embedded MCU. Okay, so we just talk about Strongbox, which is a GPU-TE. So also, we can do a category for the two types of GPT existing for the SOTA. So in general, we can categorize into two types. The first is called Shin-style GPU-TEs. Okay, basically for those style GPUs, it protects the critical components and only. And the examples like Strongbox, like a Cage, like Mighty, those are the Shin-style GPU-TE. The other type is called a VM-based GPU-TE. For this type, actually, we can have recent work like ACAI, and also NVIDIA has a confidential compute, and those kind of architecture, they belong to this VM-style GPU-TE. Basically, it leverages a CVM on the CPU side and to communicate with the GPU. Okay, I mean, the pros for this approach is out-of-box compatibility. However, it introduces high TCP and also larger attack surface. Okay, let's move on. Let's first take a look at the Shin-style GPU-TEs. So basically, for the Shin-style GPU-TEs, it only protects security-related components. And other components like power management, GPU initialization are actually not protected. So the question here is, if those unprotected components become malicious, are they threaten the security of GPU-TE? So that's a research question we want to answer. So before we answer that question, let's first take a look at how Shin-style GPU-TE works. So the first step typically is we can encrypt the data to prevent data driver from stealing. Second, we are going to protect the data with some access control. For example, we can protect it with those kind of stage 2 MMU, or we can use the confidential computer architecture to do the protection. Basically, we pretend those kind of data to be modified by the malicious OS. Third, the GPU will decrypt the data and they will be executed on the GPU side, okay, as a plain text. Okay, so we can see that the data could be in the two status. The first status is encrypted by those kind of encryption algorithm. The second one is actually protected by those kind of access control. So here the question is, so what things could go wrong? All right, so here for the Shin-style GPT, actually they made an assumption we think is invalid. The assumption is that the unprotected components are either one-time routes or security irrelevant. The reality is unprotected components are not always safe. For example, early GPU actually they take care of computation, the CPU take care of the things like scheduling. And also modern GPUs actually they embed a microcontroller unit, MCU, in the GPU. And the CPU actually can put data into the memory. Okay. The question here is, let's say if the underlying hardware is more and more complex, can we still rely on the assumption of a Shin GPU state? The answer is no, actually. So the assumption here is invalid because the MCU actually is managed by the untrusted operating system during the initialization. Okay, so let's really take a look at the on-GPU firmware. Actually, it runs on the GPU embedded MCU, and it can be viewed by the trusted OS and SMU as a part of the GPU. So the MCU itself actually is part of the GPU. And there is no isolation between this MCU and the GPU-TE. So that's the key, okay? Okay, so in this way, we introduce an attack called Moreaes. Actually, it can break GPU-TE with this malicious GPU embedded MCU. So basically, what we do is we do following 3 steps. The first, we can load a malicious firmware into the MCU during the booting process. Okay. Second, we wait the GPU to process the protected data. Note that those data are plain text in GPU. Okay. Then third step is we can simply steal the data from the GPU memory, and we can send it out to an attacker. Okay. Okay, here is an attack demo. So basically, we we use Moreaes to tamper a YOLO version 4 protected by the GPU-TE. As we can see from the figure on your top left is the right one. So basically, we can identify 3 objects: the car, the person, and the stop sign. And for the right side, we actually can see that we can identify the car as a stop sign, and also we recognize the stop sign as a car. So that's an attack. For the figure C, actually we can see that the person and the stop sign are removed from the figure. And the last one, actually, they can move the move the location of an object. So that's basically by using our attacker, we can attack the YOLO version 4. Okay, we also get the acknowledgement from ARM. ARM says that actually in future they are going to decide to add a checksum upstream to enable downstream verification. Okay, let's do a short conclusion on Mo. Mo is the first attack against the current GPT proposals, and we can see that the vulnerable design actually is not limited to the GPU. Both academic and industry have explored this design on peripherals like a network card or USB, etc. Okay, and also we hope to raise the community awareness of risk such as hidden components. And I also believe the RISC-V community can provide a more transparency solution to those kind of Mo attacks. Also, we also have the source code on the GitHub. So if everybody interested, please feel free to download it. Okay, for the last part, I'm going to very briefly introduce our university and our lab. So I'm from Southern University of Science and Technology, which is a beautiful university in Shenzhen, China. And also SOSTEC is a pretty relatively new university. So it's, I mean, the weather probably is similar to here because we don't have much days for winter, okay? And actually, I'm running a lab called Compass. It's a computer system security lab. And we do cutting-edge security, we do cutting-edge research in system security and hardware-assisted security and trusted execution environment, etc. So I'm sincerely invite everybody, if you have time, please feel free to visit us, and we can chat about research, and hope we can see you in Shenzhen. So finally, thank you very much for your attention. I'll be happy to take any questions. Yeah.
Okay, any questions? Okay. Okay.
So thanks for the talk. So I'm wondering if the malicious firmware can be detected by the secure boot or technologies similar like that, because I guess that if the GPU support T, then the entire booting process should be protected by the secure booting, right? So can the secure booting protect from loading a malicious firmware?
Yeah. I mean, the quick answer is yes. Actually, if we do the verification during the booting process, definitely we can see that if it's every time loaded, we can see that firmware is malicious. However, it depends. So let's say because the firmware currently the GPU we use is Mali, and actually they can load this firmware or they can replace this firmware during the runtime. So if they can replace, even let's say we protected this firmware during the GPU booting, okay, fine. But later, let's say during the runtime, if we can have some way to replace the firmware, and I mean, I hope they can do some verification also if for the replacement. But if they don't have this, it also could be vulnerable to our attack. Yeah.
Okay, thanks.
Sure, no problem.
I just want to follow up. Like it seems like if the ARM said like they will just add some like upstream like check some defense, but it seems like they can also not be able to defend the runtime like if you replace the firmware thing, right?
Right. So it depends if they can have. I mean, the checksum only says that hey, this is the correct one, but actually the implementation process is not done by ARM. Mm-hmm. It's actually done by the GPU side. So if the GPU choose not to implement those things, it's useless. Yeah.
Got it. Okay. Any other one want to ask question? Okay. If that's all, let's thank the speaker again.
Sure.
Okay. Yeah. Okay. So the third talk is from Professor Lucas Wanner, who is a professor in the Institute of Computing at the University of Campinas. His research is at the intersection of hardware and software systems, particularly in energy and performance optimization, runtime systems for embedded applications, and specialized hardware designs. So the talk he will give us today is RISC-V matrix acceleration, designing and implementing an ISA extension. Okay, cool. Okay, so let's welcome.
Good afternoon, everyone. So today I'll say a few words about our project on designing and implementing a RISC-V-based matrix acceleration extension. So, matrix operations are central to modern compute workloads. AI is matrix multiplication from our standpoint, right? In fact, major ISAs now include matrix processing capabilities. We've seen ARM-SME2, the pioneering Power MMA extension, Intel AMX, and many others. RISC-V now has matrix extensions under active discussion. There are ongoing RVI interest groups that are discussing proposals, and we have fairly advanced industry prototypes, notably from T-Head Alibaba. So what are our goals in this project? First, we want to contribute to the definition of RISC-V matrix processing standards. So we're part of these interest groups. But at the same time, we also want to build a prototype matrix engine for RISC-V. Great. So being a little more specific, wow, the delay really is noticeable. Being more specific, what we need to do is to first design a RISC-V ISA extension, right? There's no standard for matrix operations in RISC-V as of now. Once we do that, we want to develop a dedicated matrix processing unit microarchitecture. We want to integrate this microarchitecture within a RISC-V core. To do that, we need to create supporting libraries, compilers, tools, simulators. We need to build and test FPGA prototypes. And finally, we need to tape out actual silicon chips. So I'm here representing a group of approximately 20 people from the Computer Systems Laboratory at Unicamp, our partners at Eldorado, Barcelona Supercomputing Center, and our industry partner, HIT. So I have a fairly large group of people working on this project. So to give a very broad overview of what we're doing, here I'm showing a standard RISC-V core tile with its instruction and data caches, its scalar registers, its functional units, possibly a vector processing unit, right? And what we're targeting here is adding a whole new tile attached to this core tile that'll be responsible for working with matrix operations. So, the RISC-V core will decode instructions, send out commands, effectively decoded commands to this MPU tile, which will then be issued and ordered and completely executed, completely handled by this MPU tile, which means that this MPU tile will directly access memory, right? It will not rely on the core for memory accesses. So memory loads and memory stores will be handled directly by this MPU tile. And effectively, this will be functional units to do computation, and a whole lot of area for storing tile data, for storing matrix data, right? At some point of the memory hierarchy, this MPU tile will share some memory with the core tile. That's likely going to be at the L2 cache level, for example, right? It's probably not a good idea to have them share data all the way out there in memory. If we zoom into this MPU tile a little more, what we're looking at here is adding several new registers for tile data. So a matrix register bank. In keeping with scalar registers in RISC-V, with vector registers in RISC-V, in our ISA extension, we added 32 new registers from M0 to M31. And then the functional units are going to perform operations between these registers, right? They're going to perform operations between two inputs, possibly a third input, that's the output itself, right? So A operation with B, operation with C, they'll be stored back into C. If we do, for example, a matrix multiplication, that means we'll need to load 2 small tiles of a whole large matrix. We load them into registers, and these registers A and B here, M1, M2. We multiply them, we store them back into matrix C, into small tile C, more precisely. And that's, with these operations, we can multiply a whole matrix. The difference is that instead of working on a single element, we're working on a whole tile at a time. So these 32 new registers, they'll hold an n by n matrix. So for example, if it's a 4 by 4 matrix, I have 4 rows, 4 columns. Of course, like vector registers, we're not dealing with a single data element anymore. We're dealing with several data elements. But unlike vector registers, now we have 2 dimensions, right? So we have to have a row length, that is how long in bits each line is. We have an element length, as we do with vectors, right? That determines how many elements are in each row. And then we have a full matrix length, however long this whole register is. That determines how many lines we have there. For our first version, we're targeting a 4 by 4 FP32 register, right? So 4 lines, 4 rows, 4 columns. Each element is a 32-bit floating point or 32-bit integer element. So this means an M length of 512 bits, which is fairly modest. It's comparable to what we have in vectors nowadays, which means that each line is a small vector of 128 bits. And in this case, each element, at least at first, 32-bit value. So we're not adding a whole lot of state here. We're talking about 2 kilobytes of new data being added to the processor. Likewise, our first version of this ISA, right? There is no standard RISC-V matrix ISA as of now, so we designed our own, right? And this first design is a minimal instruction set for gem operations. This is enough, all that we need to perform, full matrix multiplication. These are all new RISC-V 32-bit instructions that are under a single matrix operation code. We'll need some space in the instruction encoding. And within that space, we'll have at least 4 different instruction formats. First for configuration setting, then for memory accesses, loads and stores, register movement, for example, moving from one register to another, zeroing out a register, maybe transposing a register, and finally the important ones, the arithmetic operations. So if we zoom into what we need to do for loads and stores, we essentially need to load a whole block of data from memory now, right? It's similar to vector, but again with some particularities, right? Typically, when we store a matrix in a C program, we're storing in row major format, right? Which means that, for example, if you're loading this 4 by 4 matrix into 2 by 2 registers, the data from the registers may be interspersed within memory, right? We may have, because we're storing a whole line, then another whole line, then another whole line. And then when we want to do load for this first register, we're zooming into a corner, right? Which means we need line stride access for standard access, right? As you can imagine, that can get inefficient really quickly, right? Because we need to do several memory bursts to load a whole matrix register. So of course, we also support contiguous unit stride or non-strided access, right? Where the data for each tile is already packed in memory, is already stored in an optimal layout in memory. If you look into arithmetic operations, essentially here now we have register-register operations as a standard in any RISC architecture. So we have some operation that stores into a matrix destination register from 2 source registers. Of course, the destination register may itself be a source, right? If you're doing a MAC operation, for example. Essentially, you have add, subtract, multiply, and accumulate. And I just wanted to highlight this encoding here to show that there's not a whole lot of space within the encoding of instructions if we allow for many registers. Right? We're spending 15 bits here just to address our registers. They're quite limited in how many operations we can support here. So to extend this, at some point we'll either need some state, as in configuration registers, CSRs, or we'll need to expand the instruction size. There's no way around this. We need more information than what we have here if we want to support a whole set of new instructions. So let's just look at a small example for an operation. Right? Imagine we want to do, the main operation is MAC, right? So we're going to perform C equals C plus A times B transpose. We always assume B has been transposed prior to loading. So this row of B is actually a column of B. So the operation that needs to happen is in this 2x2 register example, we need to multiply first row by first row by second row by first row, second row by first row, right? So it's the whole combination. It's a cubic operation for matrix multiply. There are many ways to implement this in terms of microarchitecture, right? A potentially very performant way to implement this is a full parallel operation, right? Where you do all the multiplications at once using dedicated multipliers, which means that for an n squared register tile, right, we'll need n cube multipliers. So if you have, for example, 4x4 registers, we'll need 64 multipliers to perform this operation completely in parallel, right? Again, this is not the only way to implement this. We could do some serialization here. We could do individual rows by individual columns, but then we'll naturally take more cycles to complete this operation. Once we do these multiplications in parallel, we need to do a reduction here, right? We need to sum up the elements and then finally accumulate with whatever was on the destination register already, right? If we think of latency for this operation, one way to think of this latency is however long it takes to do a multiplication plus log of n, where n is tile size, because we need to do this reduction tree, plus 1 to accumulate in the final step. So in our V0 prototype of 4x4 registers, 64 multipliers, this is the implementation we chose. We're looking at a latency of 5 cycles to perform this MAC operation. My fonts are a little strange here. I think but I think it's still readable, right? So how does software look, right? We have a typical triple loop for matrix multiplication here, working over tiles, right? As we do with when optimizing for cache anyway. But the difference is instead of loading single elements accumulating into C, what we're going to do is zero out a full matrix register with that MZ, M0. That means zero out register 0. We have 2 pointers for tile A and tile B. We load them into the matrix registers. We do the MAC operation. We continue iterating over C. When we're done, we store C, and we're done with that small block, right? Then we move on to the next tile, to the next block. So in terms of software, it's very similar. If you want to be naive, if you want to be a little more optimized, you probably have to do some unrolling here, right? So we want to work over a large panel, a larger subpanel of matrix C. The idea here is that instead of just working on this small block here, you try to load more registers, you try to accumulate over a larger set of registers, right? That improves compute intensity. You do more operations per each load that you do, right? You reuse data that you already loaded into registers. So potentially very good, if not optimal, configuration is to use, for example, 5 input registers for A, 4 for B, and then 20 registers to accumulate over C. What we actually want to do is always maximize this accumulation, right? We need to allocate more registers for accumulation because that's what stays stationary. That's what stays within the registers. If you compare, working over a single tile of accumulation versus working over 20 tiles of accumulation, we get a proportional improvement in compute intensity. Our current microarchitecture, as I said, has a matrix functional unit that executes 64 max in 5 cycles. So that means a throughput of 12.8 max per cycle, which corresponds to about 38.4 gigaflops at 1.5 gigahertz. This is more or less equivalent of a single AVX unit at equivalent frequency, right? AVX units work at maybe 4 gigahertz. If you look at what can be a potential bottleneck for performance here is actually feeding the functional unit with data, right? Memory latency can limit sustained throughput for this unit. So really our performance goal from a modeling and optimization standpoint is to maximize functional unit utilization. We want to get as close to using the functional units 100% of the time as possible. If the functional units are idle, we're not performing. That's the key point. So the strategies here are, as I said, we'll use large panels to increase this compute to memory ratio, do more compute per memory access. We have some fancy, software pipelining and prefetching. This is still, code that needs to be handwritten, very finely tuned to try to, put some distance between the loads and actually using the registers. And it's an obvious conclusion, but of course we need a small cache for this MPU. We did a lot of work here to realize, caches are actually very important. So we do need a cache dedicated for the memory processing unit. So let me just show you one single result here, an evaluation scenario based on Gen 5 simulation, where I have a single matrix engine with one functional unit, so just kind of the smallest version of this hardware, a model at 1.5 gig frequency, using fairly old DDR4 memory with a small cache for the MPU and a slightly larger cache shared with the standard RISC-V core. What I'm showing here in this plot is on the x-axis input sizes of the matrix, so M and K, all dimensions are the same, right? So as we go along the x-axis, matrix sizes are increasing, and on the y-axis, I'm showing performance in gigaflops. The red line up there is peak performance, right? If the functional units were running all the time, we get those 38 gigaflops per second. The gray line way down there is if we take the standard open blast approach and accelerate it with the MPU. Using large panels, using whatever minimal optimization we can do, but still relying on the open blast tiling and caching strategy. Right? So the standard stuff doesn't quite work because it's fought for vectors mainly, right? So once we move to tiles, this packing that's called cubically within Open Blast essentially doesn't quite work for us in the MPU scenario anymore. So we actually get around 60% of maximum performance, even when matrices are large. If you do some optimized packing that's fought specifically for the MPU, right? So the idea is that we want to avoid those strided loads, right? We want to load a contiguous block into the matrix registers. So we have a packing step before going into the matrix multiplication kernel, but we're adding that here, right? We're discounting this for performance counting. If we do that, then we can reach about 90% efficiency, which is getting pretty reasonable, right? Because if you think about it, we actually have some scalar instructions mixed in the matrix multiplication kernel. We still need to do pointer accounting. We still need to do branches and so on. So we'll never reach 100%. Now, if you only had to do gem, right, even with those scalar instructions mixed in, we get around 95% efficiency. Right? So we're quite comfortable with this at this level. With the small functional unit, we think we can achieve pretty good performance. But yeah, 90% of peak performance. But we still have a lot of stuff to do, right? So what's our status as of now? We've completed the basic software stack. We have QEMU, Gen 5 simulators running this stuff. We have the optimized blast libraries. We have benchmarks applications. But as Professor Guido hinted this morning, next year, and then ongoing work, we want to have full LLVM compiler support for this stuff. This is very important, right? We don't want to have that handwritten code that only one of our students can write and understand. We want to actually have the compiler generate this code optimally. In terms of hardware design, we've completed the RTL microarchitecture. We're working on the final details for an FPGA prototype. Most of the stuff is running. We still have some things to work out. This year, our aim is to tightly integrate this with the RISC-V core. As of now, it's kind of a side unit to the RISC-V core. And next year, we'll move on to actual circuit fabrication. In terms of the ISA, right, as I said, we worked on a minimal ISA. So we need to support more data types. We need mixed types. We need widening. we need configuration either through CSRs, or we need to have larger instruction words. We need to have masks to work over arbitrary data sizes. So there's a lot of limitations on the ISA side of things. And we'll work on those, but ultimately, whatever we do in terms of the ISA design doesn't quite matter, because in the end, we'll have to have compliance with whatever standard comes up from RISC-V, right? So we're contributing to those discussions, but our ultimate goal is not to have our own matrix ISA, it's to comply with the RISC-V matrix ISA. We're just taking our best guess into the directions where this ISA is actually going to go. For the microarchitecture, we want to explore alternative computation models. As I said, we have this full parallel implementation. It's very performant, but it's very expensive as well. So we want to look into different models, for example, based on order product of vectors. From our standpoint in microarchitecture, we need to model, simulate all these parameters, such as what happens if you have larger registers but fewer of them. What happens if you have multiple of these functional units within a core? Or if you have multiple MPUs working in parallel, right? So that's all things we want to explore in the near future. So that's what I had today. Thanks so much for listening, and I'll be glad to take any questions.
Okay, question from the audience.
Okay, so thank you for your presentation. Really interesting. It was not clear for me because you have shown 1.5 gigahertz. Is it correct? Can you put there, please? Yeah.
Remember, we're talking Gem5 simulation. This is not running on the FPGA, right? On the FPGA, our frequency is much lower. Right?
Yeah, this is the point.
That's what we hope we can achieve reasonably when we move to IC.
Okay, so 1.5 is what you've got in the simulator? Yeah.
No, again, this is Gem5 simulation. So Gem5 is a high-level cycle-accurate simulator. Mm-hmm. So we have to model a frequency, right? 1.5 is what we expect to reasonably attain with our current design.
Okay, and in the you did the RTL. Do you have already some simulation?
Yeah, so all the stuff, the units themselves are working. All the stuff is fine. It's the integration of the software that's still a little, have some kinks to be worked out.
Okay, nice. Thank you.
My question is on the same line as hers. So you mentioned that the benchmark was made using this cycle-accurate simulation. My question is, what assumptions did you make it to perform this benchmark? Like, what micro-architectural decisions were made in this simulation?
So for the core doesn't matter. That's the important part, right? Because again, the core is a blip within these, the scalar core, I mean, is a blip within this evaluation, so it won't change much. But simple scalar core, a 5-stage pipeline, no out of order execution. But all that matters really, what dominates time here is the MPU.
Excuse me. I have one more question, if I'm allowed. What if we were making? I mean, you are already implementing a prototype in FPGA, so you probably will have these results later. But what do you think would be the implications after we implement this matrix extension in hardware? Like, would there be performance implications that were not captured by this simulation?
Yeah, sure. There definitely will be, not just the RTL implementation, but the node itself, the technology node itself may determine some limits on what we can achieve in frequency, and even the area we can have. As I said, the intention is not to have a single one of these, but many of these working in parallel, or to have larger register, beefier functional units. So there will definitely be constraints posed by the actual implementation. But again, I think this scenario we have here from what our preliminary data, this seems reasonable, that we can achieve for this small unit, we can achieve a fairly high frequency.
Okay, thanks.
Okay, due to time limit, I think maybe take it offline, okay? So yeah,
Thanks so
we
much.
have to move to the next slide. Okay, yeah, let's thank the speaker again. So you can go ahead and set up. Yeah, for the final talk is Dr. Liu Shan from the from the Beijing Institute of Open Source Chip. So she's a senior hardware design engineer and now works at the SoC emulation team at the Beijing Institute of Open Source Chip. Her expertise spans over many topics like external memory system, SoC architecture, network on chip design, SoC emulation, and FPGA-based verification and acceleration. So the talk she will give us today is about Xiangshan, especially the Xiangshan computing subsystem solution. So. Okay, we'll wait for the slides to be downloaded because there's some format issues of the if we play it online. Okay, 10 minutes to go. Oh, sorry, 10 seconds.
Sorry for the delay. Good afternoon, everyone. I'm Shan Liu from Beijing Institute of Open Source Chip. You can call us BOSC, with 7 years working experience in semiconductor industry. Today, I'm going to present Xiangshan Compute Subsystem Solution at BOSC. Yeah, the agenda for today. First, I'll give a quick background about BOSC. Next, we'll dive into the Xiangshan CPU solution with technical details. Next, I'll show you the network on chip solution at BOSC. Finally, our compute subsystem solutions. Background. So who are we? To those who don't know BOSC, our first mission is to develop open source and high performance RISC-V CPUs. That is our Xiangshan CPU family. On the left-hand side, you can see This is the single thread spec CPU 2006 performance with ARM, RISC-V, CISC, Intel cores performance numbers. x86 is here. It's my laser tag. Oh, okay. Yeah, on the right side is the Intel Xeon CPU. It's about 19.73 per gigahertz performance. The green bar shows the performance per gigahertz. The purple bar shows the total frequency. On the left side, left part is the ARM CPUs. You can see the ARM N2 is about 15.7 per gigahertz, and ARM V1 is about 16.82 per gigahertz. And where is RISC-V? We are in the middle. Here I listed some common RISC-V products in the market, and I highlight our Xiangshan products, with 3 generations. We start from our first generation, Yanxihu, that is around 7 per gigahertz performance. Then we have our next generation, Nanhu, around 10 per gigahertz performance. And this year, we released our Kunminghu, 3rd generation Xiangshan core, that is 15 per gigahertz performance. So another clear view to compare with ARM CPUs, you can see our first CPU core, Yanxihu, that is almost competitive to ARM A73. And our second generation Nanhu is competitive to ARM Cortex A76. Our 3rd generation Kunminghu, which almost the same as ARM N2, which is, we always think if it's around or over 15 per gigahertz, that is the high performance CPU. The second mission is to build up open source RISC-V ecosystem. Though I won't dive into the details, but I want to give you the whole picture of BOSC. So it includes 2 parts. On the one hand, we develop infrastructure and tools. On the other hand, we provide chip design methodologies like open source verification and agile development flow. So that for the I feel like there is delays of my click. Sorry. Oh, okay, sure. Yeah. So the why we want to do this, because we want to lower the customization of a design. So within the ecosystem, we have open sourced CPU cores, we have open sourced EDA tools, and we are also working on open source verification methodologies and open source simulation tools, and with compiler to further optimize RISC-V cores. Finally, the effort for customization is like this small. This is our second mission. The third mission is to provide Xiangshan compute subsystem solution. What is exactly a compute subsystem to those who are not familiar with CSS? You can think it as a modular hardware block. It contains the core components for computing platform, including CPU cores like Xiangshan and memory, for example, DDR4, DDR5, high bandwidth memory, peripherals such as PCIe, DMA, interrupt controller, and all of these are connected or communicate through a network on chip. Usually, CSS is self-contained, configurable, and reusable to different design chips. This is our third mission. With this background, I think you have enough knowledge to look into our CPU family. Again, we are working on high performance open source RISC-V CPUs. With different product line, we are targeting data center, laptops, mobile devices, intelligent driving, etc. scenarios. And we already evolved through 3 generations since 2021. This diagram shows you the performance evolution of Xiangshan CPU. We start from 2021, our first generation Yanxihu, around 7 per gigahertz performance. Nanhu, our second generation, arrived in 2023 with 10 per gigahertz performance. And Kunminghu V2 planned to be launched this year, in August. That is targeting 15 per gigahertz performance. And looking forward, we are already working on Kunminghu V3 that is targeting 2023 to be released with 22 per gigahertz performance at 5 nanometer process. Here is our GitHub link. You can almost find everything here: the RTL code, the documentation, and our open Xiangshan community. So welcome everyone to check the link here. So to stress, our first generation Yanxihu, 7 per gigahertz performance with 1.3 gigahertz frequency, is end of life already. And the other 2, Nanhu and Kunminghu, are actively under development and verification. Nanhu is our second generation with balanced performance and efficiency. Kunminghu is our ultimate performance comparing to ARM N2 solution. Here is the feature list to help you understand our CPU core better. Given the time is limited, I won't go through all the features here one by one, but some features worth highlighting here. For our Nanhu and Kunminghu CPU cores, it support both Xe4 and Chai protocol, makes the CSS solution possible. Either you can use our NOC solution or you have your own NOC solution you want to plug in our CPU cores. That is possible. And our Kunminghu second generation is aligned with RVA23 profile with vector extension and hypervisor extension supported. This is the PPA number of our Xiangshan family. Yanxihu is taped out in July 2021. Nanhu is taped out in March 2023. And Kunminghu is targeting this August to be delivered and taped out. I also listed the process node, area, power, and frequency. You can see the trend from time. With time goes by, you can see the area is getting smaller and smaller. Power consumption is getting lower and lower, and we have better, higher, and higher frequency. Some successful tape-outs of our Xiangshan CPUs. Yanxihu Silicon returned in January 2022. You can see the chip on the left side and the board on the right side. And here it demos the SSH into the Debian on Xiangshan and run a GUI program via X11 forwarding. Nanhu Silicon returned in October 2023. The left side shows you the picture that we demoed during last year's RISC-V Summit in Hangzhou. It basically running it was running a desktop Linux and a streaming game through a remote cloud. The left side is the Ruyi laptop developed by SCAS, but with our Nanhu core inside. Okay, those are some general introductions of Xiangshan CPU family. Now let's dive into the technical details. First generation, Yanxihu, that is 11-stage pipelines with six wide decode and rename. We have multiple branch prediction algorithms, TAGE, statistic corrector, and the loop predictor. We have 160 integer and floating point register files separately. We have 192 entry reorder buffer, 64 entries load queue, 48 entry store queue. For each functional unit, we have a 16-entry reservation station. As for caches, it has 16 kilobytes L1 I cache, 32 kilobytes L1 D cache. Besides, it also has a 28 kilobytes L1 plus cache for instruction. Finally, we have a inclusive 1 megabytes L2 cache. This is the first generation Yanxihu. Second generation Nanhu is developed based on Yanxihu. Here I listed some key upgrades and new capabilities of Nanhu. Firstly, we decoupled the instruction fetch unit and branch prediction unit for better performance. We increased the capacity of TLB, Dcache, and LSU entries. We almost redesigned the L2 cache from inclusive L2 to non-inclusive L2. And this time we introduced a L3 cache that is 6 megabytes. For backend, it is also improved with better scheduler, instruction fusions, move elimination, etc. ISA-wise, Nanhu support bit manipulation and crypto extension. We also support physical memory protection and configurable PMA. Kunminghu, the optimization strategy is similar to Nanhu but more advanced. It also has a decoupled front end, basically the IFU and BPU, to reduce fetch bubbles and make it instruction prefetching friendly. We have aggressive outstanding instruction window with large ROB, load queue, store queue. As for cache, we have closely coupled load store pipelines and L1, L2 cache with highly banked designs. Besides, it has multi-level composite prefetching it results in low latency and high bandwidth cache access. ISA-wise, again, it supports vector and hypervisor extension aligned with RVA23 profile. This lists the performance details of our 3-generation CPUs on spec CPU 2006 for both integer and floating point. You can see Yanxihu is around 7 per gigahertz for both integer and floating point workload. Nanhu is 8.47 for spec int, 9.71 for spec FP floating point. Kunminghu is still under active verification and PPA twinning. Now we can achieve 14.72 for integer, 14.87 for floating point. At the last part of this section, I also want to mention our Xiangshan compiler collection. We have a very high performance compiler that is to further optimize our CPU performance, not only for Xiangshan, but for other RISC-V CPU products. It is built based on LLVM. You can see we branch from LLVM 19.1.0 and we do the optimization. Though all the optimizations are micro-architectural level optimizations, including memory access twinning, loop unrolling, auto vectorization, etc. And we contribute back to the LLVM mainstream, as I showed here, to LLVM 21.1.0.0. When our XSCC paired with Kunminghu, this is the highest performance we can get. We can see we are 20% better for spec int and 19% improvement. We can see the 19% improvement for floating FP, for spec floating point. So that gives us 19.32 for spec int per gigahertz, 17.94 for spec FP. This is compared with the baseline LLVM 19.1.0. As I mentioned, XSCC not only works for Xiangshan, but for other popular RISC-V products. Here are two examples. One is we apply our XSCC compiler on Space Mint X60. You can see the improvement for FP is around 30%. Oh, sorry. Yeah, for FP, I don't know why the number is not showing here, but yeah, it's almost 30% for spec int, and if I remember correctly, 19% for floating point. And also we see the improvements on Xuantie C920. So that is the Xiangshan CPU. Now let's move to our network on chip IP. Network on chip IP. What is the role in a computer subsystem? You can think it as the communication backbone, which enables data move efficiently between CPU cores, last level caches, memories, peripherals like PCIe, DMA, etc. Here I list some common topologies of network on chip or interconnect with some trade-offs you can see in the chart. Crossbar is the simplest form, right? Each source has a dedicated path to every destination, so the latency is definitely low, but the scalability is really poor. Ring, it connects all the components in a closed loop and data hoop from one node to the next. So it is very simple. It's a simplicity, right? But you can tell with the system growth, the latency increases. Mesh is like a 2D grid with all the nodes connected on the square, green square. This one is with high scalability. So that if you have a large computer subsystem with multiple cores, this could be a good choice for you. And it has moderate area and moderate power efficiency. At BOSC, we provide both ring bus options and mesh options depend on the design needs. That is our Zhujiang ring bus and Wenyuhe NOC. I will talk about them later. So Zhujiang ring bus. The picture is really clear, right? You have your CPU cores, SLC and Snoop filter, external memories, peripherals, all connected on the ring. We also support chip-to-chip connections in our Zhujiang solution. Here listed some technical indicators. For the protocols, Zhujiang support Chai Issue E, XE4, XE4 Lite. It supports configurable cache, last level cache, up to 32 megabytes. 32 megabytes. Yeah, right. And we have configurable ports, up to 32 ports in total. For coherent ports, I/O coherent ports, peripheral ports, we support up to 16. And for memory ports and coherent management ports, we support up to 8. For chip-to-chip ports, we support up to 4. This is the current PPA status of our Zhujiang ring bus. Again, PPA is still under iterative optimization, so this is just the current number I got from our development team. On the left-hand side shows you the a CSS with 4 Nanhu CPU cores, with 2 megabytes times 4 last level cache, all connected on our Zhujiang ring bus. This is the floor plan. And the PPA number is on the right-hand side. It is estimated under 12 nanometer process. The total area is 30 millimeter square. Frequency, we can almost achieve 2 gigahertz. If each port is configured at 256-bit, the per port bandwidth is 64 gigabytes per second. Oh, sure, okay, yeah. Wenyuhe V2, this is our mesh solution. Wenyuhe V2 is introduced in the China summit last year in Hangzhou. So this is V2 version, enhanced version. I'll quickly go through the technical numbers, indicators here. It's up to 12 times 12 mesh. The protocol is Chai issue E, configurable SLC from 256 kilobytes to 4 megabytes. These are some general support like POS, POC, and we support up to 16 DDR bridges and I/O masters and slaves. The PPA number of Mingyu Gao is estimated under 7 nanometer. We can now achieve 2.6 gigahertz. And here only shows you the area number of the routing node. That is the blue square used to connect it to CPU core, last level cache, or external memories, peripherals, etc. Last part is the CSS solution. You now understand Xiangshan CPU, understand NOC, then you can customize your computer subsystem. So how to customize, let me first introduce our CSS roadmap to give you some sense at where we are and where we are headed. We already released 4 core CSS. This year, we are targeting Q4 to release 8 core, 16 core CSS. Next year, hopefully, we can release 32 core and 64 core CSS to our partners. So how to configure or build up your own CSS? I hope this picture explains itself very clear, right? You have your network on chip, could be crossbar, could be ring bus, could be mesh with configurable SLC in it. And either the CPU node or a CPU cluster connected through a coherent interface. If you have a CPU cluster, you have multiple cores connected to the NOC through DSU. Besides, you have Clint and IMISC in the cluster, CPU cluster. In the system, you probably need high-speed I/Os like PCIe and DMA. They are connected through the IOMMU to NOC. You have device blocks for debug and trace, APLIC, some general I/Os like general interrupt controller. Finally, multiple channels of DDR or high bandwidth memory. And for the AI accelerators or chip-to-chip, that is for our future deployment of our Xiangshan CSS. So this is an example of Xiangshan CSS, that is Nanhu plus our Zhujiang solution. It's a little bit complicated, but the idea is quite similar to the previous picture. You have Zhujiang ring bus, CPU cluster, I/O block, last level cache, device block connected to Zhujiang ring bus. And in the future, we try to enable our AI mesh clock to support some AI scenarios like embodied AI or intelligent driving, AI PC, those use cases. For verification status, now we are down to 8 core CSS, and we are working actively on 16 core CSS. This example is Kunminghu with Wenyu He NOC. It's a more complicated diagram, but try to focus on the colored block. This example shows you 2 times 4 mesh. You have CPU cluster on the top, high-speed I/O on the left, memory, high-speed I/O, non-coherent I/O at the bottom. On the right, in the future, you may want chip-to-chip connection. This scenario, again, Kunminghu with high performance over 15 per gigahertz performance. So we are targeting server, cloud chips, large-scale AI chips as our use scenarios. For verification status, this is done with 2 8 core computer subsystems, and we are working in progress on 16 and 32 core computer subsystems. I guess that's all I have for today. Thank you for your attention.
Okay. We just have time for like one very short question
Sorry.
because we're out of time. Okay. So you want? Okay.
First of all, congratulations for the whole team on this project. It's quite
Thank you.
interesting. My question is, it's just to recap a bit of the details. You are talking that the Mingyu is 1.0 RVV compatible and RVA 23 profile compatible, right? The Mingyu generation 3
Generation 3.
is
后面
RVV
不一样。
1.0.
You mean the
The
performance,
version
right?
of RVV, yeah. The RVV version is 1.0, right? For the generation 3. Just confirming. I mean, it's probably 1.0, of course. So just make sure.
You remember the slice number?
Oh nope, but that's okay. We can talk offline about that. The other question is, the tech node for that you anticipate for Comingo is 7 nanometers on
So
SMIC.
we estimate for both 7 nanometer and 12 nanometer.
When you anticipating to have the tape out?
This August for
This
deliver
August.
to our partner for tape out.
Okay.
Yeah.
And very quickly, for this 1T and the Space Mid processors, which tech nodes were used there for comparison, for your
For
comparison?
玄铁 and Space Mint.
You did a
CPU?
comparison with them, right? So what was the
Comparison.
technology node?
Oh, I don't know their technology
Okay,
node.
yeah, just want to
Yeah.
make sure that compare similar things. Yeah, that's okay. That's great.
Right.
Thank you. Appreciate it.
Okay, so that's end the session. Okay, so we probably have a very short break, and then the next session will start. Okay, thank you.
Okay. Hello, everyone. Sorry for the so short tea break. Yeah. So maybe we will start for the next session so that we will have enough time for the dinner. So today I'd like to talk about the isolation mechanism of RISC-V, the case study of Penlai. Yeah. So there's a strong demand on isolation. So the Tannenbaum said a problem. If the system without isolation, it means a problem with a clock-toid maybe affect the missile launching subsystems. Actually, operating systems do not have such kind of isolation. Actually, isolation is a major source of security attacks. So by security attacks, we say that we mean that there's a trade-off between the performance and the security. If we have too much level of isolation, then the performance penalty will be large. Unfortunately, as we can see, there is an evolution of the system. There will be like more and more different levels of isolation. So our performance tax is increasing. So there's some data to support this conclusion. So this is a figure of the performance evolution or the performance change of operating system. In the middle column of this figure, there's a green column, which is all 0, means this is a baseline. If the performance is worse than the baseline, it will be yellow. And if the performance is worse than the baseline, it will be red. As we can see, this is a different version of Linux kernel. And as the Linux kernel, the version of Linux kernel evolve, actually the performance is getting better, right? So we can see that yellow and red turn green. But after 4.0, and we can see that the performance of Linux kernel is degrading. For each row, there's a different aspect of the kernel. For example, it's like context switch, or read, or write, or mmap, or fork, and pull. And take one for example, pull. Take pull for example. Why the performance is getting worse? Because of security text. We have to consider KPTI, which is a defense defense to the meltdown attack, which was discovered in 2018. And there will also be some slab-free list randomization to defend against the heap feng shui attack. So because of this performance, the tension between performance and security, the hardware isolation features is getting involved in a very fast way. In the recent 8 years, Intel has just released the new features of isolation more than the sum of previous 49 years. And we think that hardware and software co-design will bring new opportunities to reduce the security attacks. So one isolation mechanism is called TE. And thank Fengwei's introduction, I will skip the very detailed description now. TE has been widely used in the cloud because it is described as the last defense of the system, because even if all the software, the operating system, or even the hypervisor are, be attacked by the attacker and become malicious, the TE can protect the software running inside. So the cloud has widely used the TE. And TE has also been widely used in Moreaes systems to protect sensitive data in digital payment, in facial recognition, and the DMR. Okay, so here's a brief history of TE. As we can see that during the change and development of TE, there are like 3 different types of TE. And the first is like zone, which is represented by ARM trust zone. The second is enclave, represented by Intel SGX. And third is the confidential VM. Now, let me introduce Penlai. Penlai is actually a research prototype we think that TE is very actively research. There are many different researchers doing research on TE, and we think a prototype is very good for inspiring new ideas. So that's why we developed Light for at the first place. And indeed, actually we can see that we improve the startup latency and the cross-domain latency, and we expand the secure memory size and to increase the network throughput, increase the parallel domain numbers, and we also protect the NPU inside the TE, and that's inspired many different researchers. So currently, Light has all the 3 different types of TE, as we just mentioned, the enclave style, the CVM style, and the zone style. And all these 3 types are now available on GitHub. So let me just describe some of the research projects of Light. For example, first one is the limited security memory region. So in traditional TE, if you want to encrypt the memory, you have to use a Moreaes hash tree. However, existing systems usually have very limited support for the Moreaes hash tree. And in RISC-V, the Keystone use 16 PMP, mean physical memory protection registers for isolation, which means it can only support no more than 16 regions of isolated execution environment. So in order to extend the secure memory, we propose a page table area, which means we use page table for isolation. But different from the existing systems, we require the page table to be in certain places. We call it the page table area. And we will ensure that when the memory is getting mapped, one memory of any memory of a VM, of a domain, isolated domain, cannot be mapped to another domain, so that we put the check from the runtime to the memory mapping time to reduce the performance latency. This is the first research. The second research is to increase the scalability of encrypted memory. As I just mentioned, as long as you need to encrypt to support encrypted memory, you need to use a Moreaes hash tree. However, current Moreaes hash tree can only support very limited memories, like 256 megabyte. So in order to increase the scalability, we trade for the space with the time, which means we actually support a mountable Moreaes hash tree, and subtree of the Moreaes hash tree is not active. But as long as it is accessed, the Moreaes hash tree is activated, mounted to the whole tree, and to protect the memory integration. So in that way, we can support like 512 gigabyte memory at the same time, but only 255 active memory. Okay, this is the second problem. And the third problem, as an example, is to support encrypted data across network. As long as the data in memory is encrypted, but if you want to transfer data from one machine to another machine, you still need to decrypt the data and encrypt it using SSL, transfer it through network, and decrypt it using SSL. Then you can use the data. That means the data has actually been encrypted and decrypted for 2 times. First is by the hardware, the TE, like SGX or AMD's SEV. And the second time is encrypted and decrypted by the software, the library of SSL. So that means we can only achieve like 10% of the hardware's memory bandwidth. For example, like using RDMA. So if we can support distributed security memory, then we can remove the need of software encryption. why we propose the migratable Moco tree, so that when a node needs to transfer secure memory from one machine to another, it not only transfer the encrypted data, but also transfer all the metadata for this encryption, so that the data can be decrypted on the other node without, go through the software encryption, decryption with SSL. This is third research. So as we can see that all these ideas can be implemented on Penglai's prototype system in a very easy way and inspire even more different types of ideas. So in order to make Penglai a more general used platform, we also have some technical tutorial. For example, in last year's ASPLOS and also this year's ASPLOS, we bring Penglai to the conference and have a tutorial to show how to use this open source software. And we also collaborate actively with the existing open source communities. For example, we collaborate with Intel. Intel has actually porting their UEFI to the RISC-V platform. And the project is also a part of the RISE project. So when they need a secure booting mechanism to protect their UEFI firmware, actually they use Penglai. And we now have merged together, and currently Penglai is the default protection solution for the RISC-V UEFI. And also, we think that some part of the Penglai needs dependency on OpenSPI. So we just discussed with OpenSPI, and we say, hey, how about implement these new interfaces so that we can use your interface to support Penglai. And we have a very successful collaboration, and currently OpenSPI has merged, integrated with Penglai and supports these new interfaces. And also we propose a new specification called S-mode PMP. Actually, today there are several talks mentioned about memory protection. And this specification was proposed in 2021 in RISC-V RVI mailing list. And just last month, the specification is turned into the forward state, and it should be merged into the specification this year. And in industry, we also support many different RISC-V chip vendors to enhance their security capabilities. And we also had the first trusted digital space devices, which is totally built on RISC-V and using TE to support data being processed in the TE environment, secure environment. Okay, so let me introduce the future of Penglai in the AI area. So as we can know that AI is on more and more terminal devices, because currently our mobile phone, our notebook can run LLMs. And we have successfully run mixture, which is 8 plus 7B on a phone, and achieved the, sorry. Oh, I don't know. It should be an animation. Anyway, we achieved the 10 tokens per second in the decoding phase, which is currently is a world record. And there will be a lot of different types of application based on LLM. And we will have a lot of data to send to the LLM, which is, contain a lot of privacy information. So in our view, we think that the TE and enclave is becoming more important in the LLM area to protect mobile data, which means all this data of personal data, like a screenshot, like the SMS log and WhatsApp dialogues, all this data should be protected and processed in the TE and to serve ARM in the future. So that's all. Thank you for your attention. Thank you. Not working.
Okay, thank you for your presentation. We have time for questions, please. Okay, you have one question. I have only one mic.
Okay. Thanks for the talk. Very interesting. So for this one, for using TE enclave to protect the mobile data, for this TE, which type TE do you use? And also, what data exactly you are protecting?
Okay, thanks for the question. Actually, this is an application which is much like the agent, mobile agent, which we need to record all the users' screen snapshot. And there will be a local ARM running on the mobile phone, and to process all these users' screenshot to know what user to understand the scenario of what is using by the user, and it will also get data from the snapshot, so that the ARM will be able to understand the user in a more clever way. So these are data that we are trying to protect, and the type of TE here can be very flexible. Currently, we are using the zone-based TE, so that the data will be transferred into the TE as long as it is generated. Yeah, and will never leave the TE. Yeah. Okay.
Have more questions? I have one. You mentioned before the overhead of the encrypt, decrypt the memory.
Yeah.
Have you considered, for example, hardware accelerations for encryption, decryption to reduce this overhead?
Yes. I think the question is just exactly the one we are trying to solve, because the data movement between the CPU's memory to the accelerator's memory actually is huge, right? The overhead is huge. So our distributed secure memory can support that. You only need to move the encrypted data without decryption, as long as you also move the metadata for encryption and decryption from the CPU side to the accelerator side. And they can just, they will use the same metadata for the encryption and decryption. Yes, so that will just remove the necessary of software encryption and decryption. Yeah.
Okay.
Okay.
Thank you. Have time for other questions? Okay, thank you again.
Okay, thanks.
Now go to the second talk of the session. Processor chip security architecture by who is here? Okay.
Yep.
Do you have it downloaded?
Here, see. Oops. This one. This one.
Click here. Oh, download here. This is download here.
点这个。Yes. Yep. So good afternoon. I'm Ray Ho from Chinese Academy, from the Institute of Information Engineering, Chinese Academy of Science. So I'm very glad to have this opportunity to present our work about the processor chip security architecture on the Global RISC-V Open Workshop. So first, let me introduce the background. So in recent years, CPU vulnerabilities have been, such as the Spectre variant, had been continuously exposed and affecting the commercial processors, including Intel, ARM, AMD. And the recent research reveals that the main modules of the processors all have security risks. So these vulnerabilities impact mobile, desktop, and server CPU chips, gaining significant attention from both industry and academia. So existing software defense systems are primarily based on the software, right? So by exploiting CPU vulnerabilities, attackers can bypass existing software security mechanisms, thus causing severe threats. Let me show some typical security programs. The first one, so the classical CPU design principles are usually not safe. So for example, the resource sharing, as we all know, the resource sharing is a very popular design principles in CPU, even in OS implementations, right? So most microarchitecture components in processor chips are shared, such as the branch predictor, the on-chip cache hierarchy, the memory controller, and so on. So, but for this shared resource, attackers can construct instruction sequence targeting specific entries precisely, thus enabling malicious training and perceptions. Another one is the microarchitecture components are typically designed with very simple and very fixed patterns or policies. So that may lead to so-called deterministic behaviors. Such kind of behaviors can be easily sensed by attackers. So it's also very dangerous. The second problem is current chip design flows, lack of systematically security environment and verification tools. So we need to we expect all the major of the security risk can be fixed before we tape out. But current EDA tools does not support that goals. So the third one is about the trusted execution environment, so-called TEE. So TEE is an important security features in modern commercial processors. But through the hardware support, the TEE can protect the code and the data in use, thus enabling the confidentiality and integrities. But the TEE, many studies reveal the TEE has many security issues. For example, the TEE management tasks are not secure. For example, its enclave memory management are usually handled by the untrusted OS, right? So it's not safe. The second one, the TEE, because the TEE and the normal world usually share the same physical computing resource. That might lead to many microarchitecture and architecture level side channel information leakage. And the third one is about the interrupt controller. So the interrupts are usually a very critical interface between the TEE and the normal world. But the controllable interrupt frequencies and the fixed interrupt entries can be used to construct the single-step execution attacks and other side channel attacks. Another problem about the security of the defense system itself. So usually the classical defense system assumes the OS is secure, but once the CPU vulnerability is exploited, so such kind of the first thing for the attackers to do is to do the privilege escalations, right? So once the OS is compromised, so the security mechanism can be destroyed or be bypassed. So we see the security of the defense system itself becomes a new challenge. And this chart introduces our approach. This is the typical architecture view. This one is the processor chip. It has a general computing EE environment we call the RE, and the trusted computing environment, the TE, right? And upon the hardware chips, there are the operating systems. So what we do is first, So what we do is first we redesign the existing architecture and microarchitecture components to effectively mitigate the security risks and thus enhance its security. For example, we redesign the speculative execution mechanisms with better security. And the third one is we try to enhance the security of the TE. For example, we design new components to provide effective security support for computations. For example, the TE and some kind of the hardware security accelerators. The third one is the security specific environment. We call it SEE. So SEE is basically is of some new. We design new components to provide a secure execution environment only for security tasks. For example, we deploy the dedicated on-chip security cores to run critical security mechanisms. So upon the SEE, we have a defense corner, and we deploy the root of trust and other case security functionalities on the defense corners, and we also leave many commercial security applications on the general purpose corner and as well as the user level world. So next, I will introduce the microarchitecture security enhancement. So the first one is about the Spectre defense. So we changed the unconditional speculation to the conditional speculation. So to defend the Spectre variant, one naive approach is just to block all speculations, right? So, but this kind of method usually cause severe performance loss. So what we do, we propose the conditional speculation. So in case of the instructions without security risk, we just allow their speculations. But in case of the instructions with potential security risk, such kind of speculation will be blocked. So we expand the concept of the typical classical instruction level paradigms and propose the concept of the security dependence. So guided by such kind of new dependence, we deploy the new microarchitecture components in the pipelines to dynamically monitor and figure out the speculation with potential security risk. Thus, we can filter out the majority of operations without the security risk, and then we can prevent the small amount of the operations with potential security risks. And the second one is about the sharing. So we change the share, the sharing to the controlled sharing. So as well as just I mentioned, the traditional sharing usually is usually unsafe, but the physical isolation can cause very high hardware cost. So we propose the controlled sharing by randomize the table index and efficient content encryptions to actual so-called secure logical isolations. Here is one example about the secure branch predictors. So basically, hardware assign a private key for each thread, each software thread. In case of the index randomizations, we just apply the very lightweight address randomizations. In specific, we just XOR with the key during the hardware table index. And in case of the efficient content encryptions, we just use the lightweight encryption for content during the the table update and the table queries. We also use the same method, just XOR with the hardware generate the key. The third one is about the deterministic execution. We change the deterministic one to the non-deterministic executions. Here is still the example about the secure branch predictors. So usually the typical BPU, each entry in the BPU usually has the same finite state machines that will lead to the very fixed patterns, right? So what we do is just redesign the finite state machines of BPU with the probabilistic update policies, so which can effectively confuse the perception of the attackers. Another example is about the secure cache. So we observed that the typical cache side channel attacks usually construct stable side channels by continuously ping-pong memory operations. So guided by such kind of observations, we redesign the cache. So the cache subsystem, once the cache subsystem detects such ping operations, it will actively issue the prefetch operations just to prevent the future pong operations. So we can eliminate the ping pong operations by actively prefetch operations. Okay, so next I will introduce the TEE designs. So we propose a secure decoupled TEE architecture. We call it Hyper-T. So besides the original computing subsystems, a physical isolated security core is introduced. So the sensitive tasks, such as enclave management tasks, are deployed on such kind of physical isolated security cores, and the enclave computation tasks still run on the computing subsystems, which fully utilize its computing resources. Here is some the major features of the Hyper-T. The first one is the decoupled architectures, and the second one is it has the secure memory management features. The sensitive enclave memory allocation events will be handled on the decoupled security cores. And the third one is we enhance the interrupt controllers to make it much safer, secure. In contrast to other commercial designs, so in Hyper-T, the management tasks are deployed on independent security cores, element security risk in these security sensitive tasks. Besides, Hyper-T supports efficient and secure inter-T communications, thus avoiding the potential performance overhead introduced by software encryptions. So next I will introduce the ICE designs. So the classical architecture basically is computation centric. The computation invoke the security functions, right? So we introduce the security in execution environment, ICE IP, into the classical architectures. So ICE provide a secure environment for security tasks and serve as a system's root of trust. And ICE also has the highest privilege. And yes, I know. Start up first after power on and can access all resource in the computing world, but not the other way around. So the security critical management tasks are deployed on the SEIP. For example, the key management, the security functions such as the key keep alive and some important security policies. Next, I will introduce our integration of our designs, our security defense systems on the Xiangshan processors. Here is the overview of the Xiangshan security defense. So first thing, we just enhance the architectures. We introduce the secure BPU, secure cache, and secure memory controller, and something like that. Also, we integrate the SEIP into the Xiangshan chips. And on that, we run the enclave management tasks, which support the confidential virtual machine. And we also deploy the security functions like the keep alive, the root of trust, and recorder security policies. So current status, the Hyper-T has been integrated into the new generation of Xiangshan high-performance architecture, named the Kunminghu versions. And this is we just launched the commercial confidential virtual machines on the FPGA platforms. Also, the SEIP has been also integrated. So we hopefully all these security features will be continuously integrated with the Xiangshan mainstream released versions. So okay, so that's all. I'm looking forward to more collaboration with you guys. Thank you for listening.
Thank you for a nice talk. Have time for questions? Yes.
Do you need to change the operating system to be aware of your architecture? Or can you run it unmodified?
For the Hyper-T, we don't need to change the hypervisor and the OS. But for the other security functionalities, for the microarchitecture enhancement, we don't need. For the TE, we don't need. But for the SEIP, we need to collaboration between the OS and the defense course. So we need to add some security patches on the Linux. But I think we don't need to modify the hypervisor.
Okay, thank you again.
Okay, thank you.
Now we pass for the last talk of the session, the last talk of the day by Fernando Kastensmidt from the Federal University of Rio Grande do Sul. Okay, Fernando, the floor is yours.
Thank you. Okay, good afternoon. I'm a full professor of Federal University of Rio Grande do Sul in Porto Alegre, Brazil. And this work is going to present a hard RISC-V soft core processor, but you'll see that we propose a methodology that can be applied in a ASIC RISC-V as well, and extended to other work. I'd like to thank my co-authors. This work is also in the group that we have been presented today, so Professor José Rodrigo Azambuja and Professor Antônio Carlos Beck, that we have been developed a set of RISC-V. We have been developed a system that we can actually choose among RISC-V and accelerators for AI in the edge. And also we can implement fault tolerance techniques for aerospace or applications in the automotive, as for example. So the outline is motivation, case study, radiation effects, fault tolerance, fault injection, results, and conclusion. I will be on time. I know that it's hard, the last presentation of the day. So first of all, we must know that all integrated circuits are susceptible to faults. On space, they are susceptible to high ionizing ions, yes, heavy ions, protons, electrons, and on Earth, they are susceptible to neutron interaction, alpha particles, and so on. So if we want to build a reliable system, we needed to analyze how these effects occur in the circuit and also implement some mitigations approach. The mitigation techniques, usually, they add the redundancy and they add volting and they add extra area, power, and so on. So we needed to look of trade-offs that can meet the requirement. This work specific is to implement soft core RISC-V in SRAM-based FPGAs for aerospace. So why RISC-V? As of course, we are in the conference RISC-V, we have been talking a lot about this processor, but when we talk about space, the new space, they wanted to reuse, because this will reduce time to market. Also, you have already something that is working, so it's better to you to take something that has been already tested. And adaptive solutions is very important because you are working with a system that you have some very restricted requirements in area, performance, and power. So it's important that you can actually adapt your system. For SRAM-based FPGAs, it's very good because we have reconfigurability. To use embedded soft cores, it's important to look for open source and that we have adaptability and we can work in big groups together. And so we have chosen the RISC-V for reuse. So the objective here is to propose a methodology to mitigate this RISC-V with some mitigations. This has been automatically implemented because we have in our group developed a tool that can add automatically the TMR, voting, and so on. We needed to analyze implementation because we have talked here also about verification. So what we modify, we needed to verify. And one important thing is to use fault injection to see if all the implementations were well implemented. So we evaluated by fault injection, and later on we evaluated under radiation. And we will show some results in trade-off. So for this first work, we have implemented in a RISC-V that has already been developed at URGS as well. That's called STEEL. It's an open source. It's available in GitHub. It implements the basic set of instruction, the integer 32 bits. It has also some IPs around and has a 3-stage pipeline and runs free RTOS. So when we are looking to implement soft core processors in SRAM-based FPGA, we needed to be aware that because this FPGA is programmed by SRAM, it has a large number of bits that can be upset in the configuration. So when ionizing particle hits one of the memory cells, it can flip the information, and this information is actually can be persistent, and you needed to reconfigure the FPGA to correct this bit flip. So it's very important to add redundancy, add voting to mask the fault, and later on also to correct this fault. So for that, we implemented TMR. We are going to see that there are many implementations available in the TMR, changing the granularity. We can do coarse grain TMR, we can do fine grain TMR, we can add more or less voting. But the TMR only masks the fault. It has the ability to mask single upsets in principle, but if you are actually using fine grain TMR, you may mask multiple faults at the same time. And then we add the scrubbing, which is this continuous reconfiguration of the FPGA that can correct the bit flip of in the configuration memory. So this is just to illustrate the TMR. So we have fine grain is that when we add the voting after flip-flops, it's not necessarily add after all the flip-flops, but you can actually TMR all the logic inside. It's much complicated to implement, and for sure you needed something that is automatic. And the coarse grain TMR, then you can take big blocks, can be the entire processor, but you can divide your process in many different blocks, and then add the voting as you want in that large blocks. So the question that we wanted to answer is how many voters are enough to some case scenarios when we are going to have single bit flips and multiple bit flips. So we evaluated 4 different fine grain TMR. We found out one when we add voting after every flip-flop, or for now 2, 3, and 4. We can see in the table about the area, so in terms of register, lookup tables, and the number of voters, we can see that if you use FANOUT 1, is the largest area that we can get. It increases very much the lookup tables, especially, and we can see the voters actually are really a large number. So for the full SOC, because we took this design flow that actually take the RTL design, and then we can actually synthesize or in a FPGA flow or in an ASIC flow. And in some level, we are going to add automatically this redundancy and the voters. For the fault injection methodology, we have developed a system that injects automatic faults in areas of the FPGA. So actually we can select the area, and then we injected these faults based on previous radiation experiments that we have already done. So it's like we can add only single upsets or multiple upsets, and then we can add in different shapes according to what we have collected with real data. And we use the ICAP to inject the faults. So then we have the system that monitors the fault injection, keep receiving the data, and then we, of course, we compare the golden results. Then we can see if we got silent data corruption or timeout, okay? And the timeout can be from only the processor or also the interface and the buses. So the results. For the results, we tested 2 case studies application running in the FreeRTOS. And we can see that if we choose the largest TMR, the fine grain TMR with FANOUT 1, in this case here, that's marked with the circle, we can see that is the largest area. And also, for example, the largest essential bits, that actually is a measure that we use in FPGA to see how much bits of the configuration we are using for each design. But the question is this the best one? So we can, with fault injection, draw the reliability curve to see how they compare. So first we wanted to see if scrubbing is enough. So if we take the RISC-V with no TMR at all, and then we just run with no scrubbing and scrubbing, are we going really to get a better reliability? and not necessary. So this shows us that only scrubbing is not enough. So we needed to add some redundancy. So here we can see the lines with reliability. The X is accumulated injected faults, and in the Y is the reliability percentage. And then, for example, the best one is the fine grain TMR with an out one, that is the red one, okay? And then this is with no scrubbing. So if we just compare all the TMRs with no scrubbing, we can see that there's a big difference from like fine grain with a big fan out or a small fan out as one, because we are adding more volters. But once we add the scrubbing, because the scrubbing actually reduces the probability to have multiple faults in the configuration memory bits of the FPGA, all the curves are a little bit very close to each other. So this is an interesting result because it shows that sometimes we don't have area enough to triplicate everything. So maybe we don't need to go to the fine grain fan out one, but we can choose actually a coarse grain TMR or another fan out, and maybe we are going to get a similar reliability. But then we wanted to do the radiation test. So we performed the radiation test here at USP. Very close to here, we have the Physics Institute, the Pelletron lab. So they have an accelerator of heavy ions. And we performed the test in the zinc FPGA. And the results that we got from radiation shows that actually it's important, the fan out, because when you do fault injection, we are not analyzing, for example, some of the critical areas in the buses or that go outside FPGA, or the clock tree, and so on. And especially because in the radiation environment, we will have the real amount of bit flips that can be single upsets, multiple upsets, and so on. So if we take a look here in the final curve, we can see that with scrubbing, that are the blue bars, even that we get a better reliability with the fine grain with fan out one comparing to the coarse grain. So it shows that it's better to invest in a fine grain TMR and to add more volters if it's possible. So to conclude, oh, sorry. Guess it's the delay that makes it connect. So to conclude, we show a methodology that can add TMR for soft core processors, but also this works if we do an ASIC version of the RISC-V. With fault injection, we can actually analyze in the lab very fast which are the possibilities, but we need always to go to the radiation test at the end to have the final data. And it's important also to be able to the opportunity to look for the trade-off and to select have more or less voltage, because it's not always that you are going to be able to TMR everything. And then when you don't have this extra area to TMR everything, you will need to select the most critical points to be TMR. And for future work, we wanted to implement TMR in also others RISC-V, as the NOx RISC-V and other ones like CB32. And we are actually ongoing implementing TMR in the accelerators, so like FIN, ZincNet, and systolic array. So this is already our ongoing work. Thank you.
Thank you very much, Fernando. Have time for questions? Have some questions? So I start with one. Have you considered, for example, to use partial reconfiguration to repair the area affected by the fault?
Yeah, we can do that. Sometimes I think it is a good approach if you know that a very critical block is far away from the, let's say, because when you do scrubbing, the scrubbing always starts from the same point of the bitstream. So actually the block that's located far on top left, for example, is going to be scrubbed more often than one that's far away from that point. So you can do partial reconfiguration to speed up the process to correct the faults, yes.
Okay, thank you. Other questions?
So thank you. It's Harry that I work a lot and I learn a lot with you in your past papers. And I would like to ask how you guarantee that in the FPGA, when you have a fault, it don't get through all the bits involved in the voting. And also, why do you think the measurements don't match that well what you proposed in the curves?
Okay, why the radiation doesn't match so well with the fault injection? Yeah, even we do real data in the fault injection, but the fault injections is like we only put the reconfiguration bits. We are not implementing the fault injection in the flip-flops, the user flip-flops, and then have the BRAMs that actually needed to do a fault injection separated from the BRAMs because it's a different level of the configuration bitstream. So this all brings some different points that's not exactly the same. And also the buses. The buses are very important, like, and if you wanted to connect with the ARM, we're using the XI and so on. This actually you cannot do much for that thing. We inject faults, but we are not always allowed to inject faults in all the bits that are actually susceptible. So, yeah.
Okay, thank you again.
Okay, thank you.
We have some announcements from Sandro.
Hi everyone, for the final remark before we head out for dinner. So first regarding tomorrow's programming, for all the international guests that are using our the transportation provided by the event from the hotel to the venue here. If you're leaving if you're flying out of Brazil tomorrow, we do advise you to check out early and bring your luggage with you, as we can keep your luggage downstairs with the ladies at the reception. They can